are vector spaces over the same field, say F. And home VW defines the set of all homomorphisms, vector space homomorphisms from V into W over F. We had seen that if we define the sum and scalar multiplication of elements in home VW, then it becomes a vector space. The sum was defined that if T1 and T2 are two homomorphisms, then T1 plus T2 on V1 plus V2 becomes that this is for every vector V, T1 plus T2 is defined as VT1 plus VT2, and alpha T is defined as V of alpha T, same as alpha times VT. We had seen that T1 plus T2 is also a vector space homomorphism. Alpha T is also a vector space homomorphism. And they satisfy other properties so that home VW becomes a vector space over the field F. Next question is once we have this as a vector space, then if V and W both are finite dimensional, is home VW finite dimensional? And if that is the case, then what is the dimension of home VW? So this is what we want to prove now, that the dimension of the home VW is the product of the dimensions of V and dimension of W over F. So what we prove is this theorem. So first of all, recall this what we have proved is that if V and W are vector spaces over F, then home VW over F is a vector space over F. And recall the sum. So even recall for say T1, T2 in home VW, and for alpha in F, the definition that is V under T1 plus T2 is VT1 plus V under T2. And V under alpha T is same as alpha V under T for every V in V. So this is what I was saying, that with respect to this addition and scalar multiplication, home VW, the set of all vector space homomorphisms from V into W, is a vector space over F. Now what we want to prove further is that if the dimension of V over F and dimension of W over F are finite, then home VW over F is a finite dimensional vector space over F. And in particular, what we have is that the dimension of home VW over F is same as the dimension of V over F times dimension of W over F. So this is what now we want to prove, that if the dimension of V over F and dimension of W over F are finite, then home VW is also a finite dimensional vector space, and particularly this dimension is the product of the dimensions of V and the dimension of W. So we prove this. So let us take that the dimension of say V over FB and dimension of W over FB, say M, both suppose are finite. In particular, let us take a basis for say B. So let B1 be the basis for V1, V2, and say Vn. Be a basis for V over F, and B2, W1, W2, Wm be a basis for V over W over F. So what we want to is that we want to obtain a basis now. So we want, what do we want? To find a basis. Let us say B. For home V W over F. And we hope to find this basis having m number of elements. Elements in home VW, so they are vector space homomorphisms of V into W. Now, since these are mappings, and therefore to obtain these mappings, so we need to define how they behave for every element V in V. Now, let us take V in V be arbitrary. Then, since B1 is a basis, for V over F, and therefore there exists a unique linear combination that represents V over F. So there exists a unique linear combination representing V. That means what? There exist unique scalars, uniquely determined scalars. Let us say alpha 1, alpha 2, alpha n in F such that V is their linear combination. So alpha 1 V1, alpha 2 V2, and this is alpha n Vn. So these alphas are uniquely determined for a given fixed V. All right, now define the map say Th. Define the map, let us say Tij, for every I1 to n and for every j1 to m. So let us define this Tij, the map of V to W. V of Tij, that is the image. So V going to V of Tij. So define this V of Tij as alpha I W J. So these alpha is come from this alpha 1, alpha 2, alpha n. So I varies from, so for every I 1 to n, and WJs come from B2, which is a basis for W over F, and therefore this J will take values 1 to up to n. So these are the mappings in number Mn. As I can take n values, J can take m values. What we want to prove is that these mappings actually form a basis. So let us take B to be these Tijs. So these Tijs as defined here. So these are the as defined here. So we prove that B is a basis or home P W but F. All right. So first of all, we must prove that this is a subset here, and second that Tijs are linearly independent and they do span. These are the things we have to prove. So first, this is a subset here. That means each Tij is a vector space homomorphism. Is a vector space homomorphism of V into W. Now, to show that this Tij is a vector space homomorphism, so you have to prove that uh, this preserves the sum and it preserves the scalar multiplication. So suppose S is a homomorphism of V into W, and we show that there is some S for which these two coincide, the Tij and so first this Tij of if you want to see say V plus V prime. So we want to prove that this is same as V under Tij plus V prime under Tij, and we also want to prove that alpha Tij, this alpha V alpha V of Tij is same as alpha v t I j. So for say if V is the linear combination, say alpha I V I is equal to 1 to n, and V prime is say alpha I prime, V I is equal to 1 to n, and alpha I primes, they are from F and are uniquely determined. Are uniquely determined. Okay. So when you write this, we know that what is V of Tij. So V of Tij, as we have defined, this is alpha I Wj. And likewise, V prime of Tij is alpha I prime Wj. So you can see that V plus V prime, this is the linear combination, alpha plus alpha time with I here and Vi I1 to n. And that when you apply this Tij on both sides, so what you get is V plus V prime Tij is equal to this sum alpha plus alpha I prime Vi Tij. This is Vi T I1 to n. So when you want to see V of Tij, in particular now you can see here. So V of Tij, when you are writing V as alpha 1, V1 plus alpha 2, V2. So this you can check that this is actually Wj, actually equal to I is equal to n alpha I plus alpha I prime Wj. So this is Wj that I show you just now. And this further can be written as sum of this alpha I Wj I is equal to 1 to n plus this is I is equal to 1 to n alpha I prime Wj. Now this sum तो हो नहीं रहा. There is no sum actually. Here because there is no sum, so this sum is not there. There is no sum. This is only the coefficient here that we have to write here. The coefficient of Vi, that is alpha I plus alpha I prime, and then Wj. So this is W V I T J Wj. Okay, and this is Wj. Simply sum. And this is your V of Tij plus V prime of Tij. So this Vi of Tij is Wj. Let us see. Since Vi of Tij is simply Wj for every I 1 to n. For recall that V, if it is alpha 1 V1 plus alpha 2 plus alpha n Vn. We have defined the V of Tij as alpha I Wj. Alright, this is for every I 1 to n and j 1 to n. So in particular, when you write this Vi, so this Vi becomes 0 V1 plus 0 V2 and this is 0 Vi minus 1, 1 Vi plus 0 Vi plus 1 and this is 0 Vn. So alpha I here, this is the coefficient here. So here alpha I is 1. The coefficient of Vi in the linear combination of Vi. And therefore this alpha I Wj, so alpha I Wj here becomes Wj, 1 Wj or simply W. So what we here see is that Vi Tj is Wj. So Vi Tj is Wj. You can note here that this I is same here. Now if and also you can obtain that Vi Tkj. So when you see here Vi Tkj, so when you are writing the Vi as the linear combination, so here what we find is that the coefficient we have to look for here. So this V, when you write this as alpha 1 V1 alpha 2 V2, Vtij becomes alpha I Wj. So that is alpha I Wj. So here this has to be alpha k Wj. This is alpha k Wj. Now alpha k is the coefficient of Vk in the linear combination of Vi. Now here in the linear combination of Vi, the coefficient of Vi only is 1, all others are 0 and therefore this is 0. So this is 0 Wj, that means 0. So what we have here is that when these indices are same, it is Wj, otherwise 0. So what we see here is that this Vi Tkj, this is 1 when k and I are equal and 0. And this is and Vi Tkj is 0 and k and I are different. So what we have got is that the effect of Tij on the basis vectors Vi. So what we have got is that Vi Tkj is delta Ik, okay, Wj. That means this is 1 Kiranakar delta. So this is 1 when k and I are equal. So in that case, this will be Wj and k and I are equal and is 0 and k and I are distinct. and this is for all I 1 to n, and all k also 1 to n, and j 1 to n. So this is what you can remember, that the effect of the mapping to Tij on the basis vectors. So B1 for V or F is as. So what we have seen, that this Tij preserves the sum, and also you can check that so we have seen that V plus V prime of Tij is V Tij as V prime Tij. Next, take this alpha in F, V in V. Alpha V, this is an element of this, and we want to see Tij. So alpha V is, so this is a linear combination here of V is alpha I V I 1 to n of Tij. So this is the linear combination alpha I Vi 1 to n of Tij. Now, when you have a linear combination, so say beta 1 V1 plus beta 2 V2 plus beta n Vn as the linear combination for a vector in V, how the Tij is defined? The coefficient of Vi times Wj. So this is the coefficient of Vi is alpha I Wj, and this is same as alpha I Wj. Same as alpha I Wj is the image of V under Tij. So this is V under Tij. So this is what it is, that you can see that here this is alpha V Tij, and this is equal to alpha times V Tij. So putting these two together, so this as well as this, what we have got is the Tijs are homomorphic. And so Tijs are homomorphic for every I 1 to n, for every j 1 to n. So the set B is a subset of home VW. Next, what we want to prove, that they are linearly independent and they do span the whole of the vector space. All right. So now, so this B, which consists of these Tijs, span VW over F. And for this, what we show is that any homomorphism in home VW is a linear combination of these Tijs. So let us take so for this, let us take S to be an arbitrary homomorphism of V into W. We want to show that S is a linear combination of Tijs. Now S is a homomorphism, and therefore it sends so S is a homomorphism, means S sends elements V into W. V goes to Vs. Vs is an element of W, and for this B2 is the basis. So that means this is basically is contained here in the linear span of B2. And recall B2, what was B2? The basis for this. So B2 was W1, W2, Wn. A basis for W over N. So every Vs is a linear combination of W1, W2, and so on. So in particular, each VIS is also a linear combination of W1, W2. So in particular, VIS, this is an element of W. So this is also in the linear span of P2 for every I 1 to N. Because VIS is an element of W for every VI, the basis vector B1 for V over F, and therefore this is a linear combination. So we fix this, so this is a linear combination W1, W2, Wm. So let us take that this VIS, a linear combination. So this is say alpha I corresponding to this I, and now we have J's, WJ's, W1, W2, M. And this is for every I 1 to N. So every VIS is a linear combination of W's. Okay. And what you can now see, so this is also take some suppose we have the map, say S naught. Suppose S naught is the linear combination of these Ti's corresponding to these alpha i's. So alpha ij, Tij, Tij. J is 1 to M. And I varies 1 to N. And I varies 1 to N. So what is S naught? S naught is the linear combination of Tij's. So this is alpha ij, Tij for every ij. So these S naught consists of all the Tij's here. So what we shall prove is that this VIS and S naught, they are equal. And once they become equal, that means S is expressed as a linear combination of Tij's. Now this, let us say VIS. For every, so let me rewrite in the next page. So what we have is that VIS is a linear combination alpha I, and corresponding to this is alpha ij, wj, j1 to m, j1 to m. And what we have defined is this S naught as the mapping. So this is 1 to n, and j is 1 to m. This is n, this is m of alpha ij Tij. And we show that S and S naught are equal, and that will make that S is a linear combination Tj's. Now we show that these they coincide for every basis vector here. So for, let us say, Vk. So Vk of S, let us say if we have to compute, and Vk of S naught, both we compute. So Vk of S naught, let us say. So Vk of S naught is Vk under this here I1 and A1 m, and this is alpha ij Tij. Now we know that these are the linear homomorphisms Tij's. So this Vk can be pushed inside. So this is summation I1 to n, summation J1 to n. And this is alpha ij Vk Tij. This is what we. Now you remember that Vk of Tij, Vk of Tij, when k and I are equal. Now here index that varies is I. So in that case that is 1. So that becomes Wj, and I is equal to k, and is 0 when I is different from k. So the sum will stay only on j. So j is equal to m. So when I becomes k, then the coefficient here is 1, otherwise 0. So this alpha ij, I becomes k, so this is alpha kj, and vktij becomes wj. So this is what it is. So this is alpha kj wj. Now we have defined this s on vis as alpha ij sum over j wj. So when you replace I by k, this is same as Vk of S as alpha kj wj is sum j1 to n. So this is actually equal to Vk under S. So you can see here that this Vk of S naught and Vk of S, they are same for every k 1 to n. So what we have got is Vk of S naught and Vk of S are same for every k 1 to n. Now these are two homomorphisms which coincide on every basis vector, and this will imply that V of S naught is same as V of S for every V in V. And for this, what you do is that you write this V as the linear combination here of basis vectors, say V1, V2, Vn, and then use this factor that for each Vk, S0 and S coincide, and that will give you that V S0 and V S are same. And that means that S0 and S are same mappings because they coincide for every vector V in the domain, and therefore the two mappings are same. So S is equal to S0 means what? So write that S is equal to S0. S is equal to S0. So S is equal to S0 means what? S is the linear combination because S0 is this. So that makes that S is the linear combination of Tijs. So S is the linear combination of Tijs. So let me take on the next page. So S is equal to S0 means what? Then this is I1 and J1 to M, and these are alpha ij, Tij. That means B spans from VW. Since S was arbitrarily chosen from home VW, and we had shown that this is a linear combination of these homomorphisms, namely Tijs, and therefore they do span home VW. Next thing is that they are linearly independent also. So to show that they are linearly independent, we just take any linear combination and equal to 0 and then prove that each coefficient must be 0. Next, these Tijs are linearly independent. For this, let us take, there is a linear combination, say here, alpha ij, Tij, and this is, let us take j is equal to 1 to m and I is equal to 1 to n is 0. This 0 means 0 map on whole meter. So to prove that these Tijs are linearly independent, what we must show that each coefficient is 0, each alpha ij is 0. Now this is 0 means this is 0 over every v. Now since these Tijs are homomorphisms, so this amounts to saying that this is I equal to n, j is equal to m, and this v and this alpha ij v Tij. So in particular, for v is equal to vk, what we get here is that this gives me that vk of this so this means this is I1 to N, J1 to M, alpha ij, Vk, Tij is 0. Good. Now Vk Tij is when I is equal to K, then this is Wj, otherwise 0. So this leaves this sum on J only, J1 to M. So alpha when I is equal to K, so this is K, J, Wj is 0. And that happens for every K 1 to N. Now Wj's are linearly independent. Being basis vectors, Wj's are linearly independent as they are basis vectors. So what we get is that this is a linear combination of Wj's equal to 0, and therefore each coefficient must be 0. So what we get is alpha Kj is 0. And this happens for every K already. So it's 1, 2 up to N, and for every J 1, 2 up to N. So what we have proved is that they are linearly independent. So hence Tij's are linearly independent. Tij's are linearly. Tij is span. Tij's are linearly independent. Therefore, V, which consists of these Tij's, and what are the Tij's? If you recall, these are mappings here V to W, and this for V as a linear combination alpha I Vi I is equal to N is mapped onto V of Tij, where this is alpha I Wj, where B1 is B1 V2 Vn is a basis for V over F, and W2 W1 W2 M is for W over F. So that's how it was defined. And in particular, these maps Vk of Tij is delta by k, and this is the G. And that means when I and k are equal, simply Wj is equal to k, 0, I and k are constant. So this forms a basis for W. And since the number of elements in B is Mn, so since the number of elements here is Mn, we get that the dimension of home VW over F is simply Mn, or Nm, better right, N and M. So this doesn't look nice. And M. This is dimension of V over F times dimension of V over this is what we wanted to prove, that home VW is also a finite dimensional vector space, and in fact the dimension of home VW is the product of the dimensions. We can simply obtain one observation here, and that is now in particular if V is equal to say W, then home VV or F is also is a vector space over F of homomorphisms of V into itself, and if the dimension is if V and W are same, then home VW is of dimension m square, where whenever dimension of V over F is m is finite. So if V is a finite dimensional vector space of dimension n, and in that case home VV is also a finite dimensional vector space, and the dimension is n square. And you can see that the basis here, a basis here you can rewrite, so thisCij's here, so this I and J are same as so this is basis here will be basis will be here Tij, I and J are equal, so Tii, and this is I is 1 to m or n, whatever. And this Tii you can simply write as Ti if you. So V of Tij, if you remember, so if V is the linear combination, this is say alpha I1 m, then V of Tij, you remember how was it defined as alpha I Wj's. So here this will be, so when you write this as a linear combination, so you can say only better. J is also m. So this is defined as V of Tij as alpha I Wj, and J also varies 1 to m. And these mappings will be m square in number, because I takes values 1 to m and J takes values 1 to n. Further, if W is F and dimension of V over F is finite, let us say this, then the dimension of home VF over F is simply m into 1, and that is n. And this is same as the dimension of V over F. So next time when we meet, we shall be more interested in home VF, and this home VF over F is called dual or dual space of V over F. So we shall start from the dual space F, and the elements are called linear functionals. So we shall stop here and we shall meet tomorrow morning. So thank you very much for your kind attention.
Thank you.